It's a terrifying sight. A 500-foot-tall tower crane swaying 2 or 3 feet in a hurricane-force gale. That engineered sway looks unnatural, but it's the first clue to its survival. Because while these multi-million-dollar machines are designed to live in the sky, they are at the absolute mercy of the wind. Get it wrong, and they come crashing down. In 2019, a crane in Dallas was ripped apart by a storm. During Hurricane Irma, at least 2 cranes in Miami collapsed under the storm's peak winds. So what is the brilliant, counterintuitive secret that keeps thousands of cranes standing while others fail? And what was the fatal flaw that made the difference? Before a crane can perform its most brilliant trick, it must first be a monument to brute force. The first layer of survival is passive strength, an engineering fortress designed to withstand forces that would level a house. It begins with the steel. The mass sections and jib are not made from ordinary metal. They are fabricated from high-strength structural steel, typically A572 Grade 50 or higher. This provides a minimum yield strength of 50,000 pounds per square inch. For an engineer, that number is critical. It means the steel can endure 50,000 pounds of force on every square inch before it starts to permanently bend or deform. Standard structural steel might yield at just 36,000 pounds per square inch. That extra margin is the difference between bending and breaking. This specific steel is chosen for its immense capacity to resist not just a constant push, but the violent, dynamic loads of a storm. The sudden gusts and cyclical buffeting that cause metal fatigue. But pure strength is heavy, and if used incorrectly, can actually make the problem worse. If a crane were a solid steel tube, it would be a death trap. The immense surface area would act as a massive sail, catching the full, unmitigated force of the wind. Instead, the entire structure is an open truss or lattice design. This is an elegant and ancient solution. Like a chain link fence versus a solid wooden one, the open framework allows wind to pass directly through the crane. This simple choice slashes the overall aerodynamic drag, preventing the mast from absorbing the wind's full energy. It reduces the wind pressure on the structure by a massive factor, making it far easier to manage. The jib, the long working arm, is even more refined. Its lattice is specifically an aerodynamic design, sometimes featuring wind spoilers to precisely manage airflow. This isn't just about drag, it's about preventing a silent killer, vortex-induced vibration. This is a phenomenon where wind passing over a structure creates alternating low-pressure zones, or vortices, that shed off the back. This shedding can create a rhythmic, sideways push, like a giant, invisible hand plucking a guitar string. If that rhythm matches the crane's natural frequency, the vibration can amplify itself uncontrollably, growing in intensity until the structure literally shakes itself to pieces. The aerodynamic open lattice design breaks up this resonance, keeping the structure stable. Finally, all of this is governed by strict, unforgiving standards, like the American ANSI/ASME B30.3. This document dictates everything from design and construction to inspection and operation. It's the industry's Bible, and it demands redundancy. This is where the out-of-service wind resistance rating comes from. These cranes are engineered to handle 3-second gusts up to 110 to 150 miles per hour, equivalent to roughly 65 to 90 miles per hour sustained winds, depending on the model and height. Every single component on that crane is built with a redundant safety factor, often 1.5 to 2 times the absolute maximum load it is ever expected to see. It's not built to handle the storm, it's built to handle a storm that is twice as bad as the worst-case forecast. This fortress of steel, advanced aerodynamics, and redundant design is the crane's armor. It's formidable, but it is not enough. It raises the question, can you ever truly over-engineer something against the raw power of nature? The armor is just there to help the crane survive its real defense, a brilliant act of complete and total surrender. The single most critical survival feature of a tower crane isn't a piece of steel. It's a procedure, a conscious, deliberate decision to stop fighting the wind and cooperate with it. It's called weather vaning. This is the entire secret. When a storm is imminent, you do not, under any circumstances, try to hold the crane still. You set it free. The process begins on the ground or in the cab. Every tower crane is equipped with an anemometer, a device that measures wind speed. It's typically located at the very top of the crane, at the apex or the A-frame, where the wind is fastest and free of obstruction. Once that device registers wind speeds hitting a preset limit, typically around 42 miles per hour or 20 meters per second, all lifting operations are shut down. This isn't an arbitrary number, it's the maximum in-service wind speed defined by most manufacturers and standards like ASME B30.3 and EN 14439, beyond which the wind load on a lifted object becomes too unpredictable and powerful to control safely, and a swinging piece of precast concrete becomes an uncontrollable wrecking ball. The operator parks the trolley and hook, drawing them back close to the mast. This is a critical step. Leaving a heavy hook at the end of a 200-foot jib creates a massive swinging mass. That pendulum effect would introduce colossal, uncontrollable torque into the mast. Bringing it in minimizes that lever arm and keeps the crane's center of gravity stable. Then, the operator performs the most important action of the day. They release the slew brake. This isn't a small component. It's a powerful hydraulic or electric braking system designed to stop the crane's entire upper assembly from rotating during normal, high-precision lifts. It's what allows an operator to hold a multi-ton load steady, thousandths of an inch at a time. By intentionally disengaging this brake, the operator puts the crane into free slew. The entire upper structure, the main jib and the counter jib, with its hundreds of tons of concrete counterweight, is now balanced on a massive, precision-engineered slew ring. This bearing, a masterpiece of metallurgy, allows the entire multi-ton assembly to rotate with almost zero friction. As gusts up to 150 miles per hour hit, the crane no longer fights. It turns. Like a massive weather vane, the jib and counter jib align themselves with the wind, presenting the smallest, most aerodynamic profile possible. The wind flows around it and through its lattice, not against it. It's the difference between holding a piece of paper flat against a fan versus turning it edge on. One gets ripped from your hand, the other barely moves. This freedom to rotate is paired with that intentional, engineered flexibility. A tower crane is not a rigid object, it is designed to sway. Rigidity is the enemy. A perfectly stiff tower would be brittle. Under a sudden powerful gust, it would absorb all the force at one point and snap. Instead, the high-strength steel mast is designed to flex. That terrifying 2 to 3 feet of movement at the top is the mast absorbing and dissipating the immense energy of wind gusts, just like a tall tree in a storm. The steel flexes, absorbs the punch, and returns to center, over and over, for hours or even days. In the most extreme cases, like a direct hit Category 5 hurricane, there is one final option: a pre-storm climb down or de-rigging. This is a logistical nightmare, a multi-day operation that is the definition of high stakes. It requires a crew to work against the clock, often in worsening weather, to use the crane's own climbing frame to remove mast sections, or even bring the entire jib down to the ground. It is a slow, multi-million-dollar decision reserved only for when the storm is so powerful that even the genius of weather vaning may not be enough. This combination of free slewing, engineered sway, and raw strength is the elegant system that keeps these giants standing. It's a fascinating paradox, isn't it, that the safety of a billion-dollar project and the lives on the street below depend entirely on a single, unlocked brake. But it is a system that demands perfection. If any one part of it fails, if the steel is flawed, if the procedure is ignored, or if the foundation gives way, the result is total, catastrophic failure. A weather vaning crane is only as good as its anchor to the earth. That anchor comes in two forms: a massive concrete gravity base or a deep foundation anchor directly to bedrock. This isn't just a slab of concrete. It can be a cube of reinforced concrete weighing hundreds of tons, keeping the center of gravity incredibly low. This mass, combined with the massive counterweights on the counter jib, is what manages the primary overturning moment. But as a crane gets taller, it needs help. A 500-foot tall crane cannot stand on its base alone. This help comes in the form of mast tie-ins. Every 3 or 4 stories, roughly every 30 to 50 feet, a heavy-duty steel collar and strut system is used to brace the crane's mast directly to the building's structural core. This is a critical load path. These tie-ins are an engineering feat in themselves, designed to allow for the vertical movement of the building as it settles under its own weight, while providing zero lateral give. As the wind pummels the mast, these tie-ins transfer that immense lateral force into the concrete shear walls of the building itself. The building and the crane effectively become one structure, fighting the storm together. But in September 2017, as Hurricane Irma's eye wall tore across Florida, this intricate system failed. Not once, but twice in Miami. A crane at a plaza construction site on Biscayne Boulevard collapsed. About 20 miles north in Hollywood, a second crane at the Hyatt Resort and Residences toppled. The jibs of both cranes snapped, leaving their arms dangling hundreds of feet over the city. These were modern cranes, supposedly rated for the storm's intensity, with out-of-service wind resistance ratings meant to handle gusts up to 140 miles per hour or more. The investigation highlighted a key vulnerability: luffing jib cranes. Luffing jibs are essential in tight urban sites because they can raise their jibs up and down, but this creates a far more complex aerodynamic profile. They have a larger sail area from the luffing mechanism and jib, making it more difficult to position them for a perfect, stable weather vane. In the chaos of Irma, the wind found a weak point, and the jibs were ripped apart. The most chilling failure, however, happened in broad daylight. On June 9, 2019, a thunderstorm cell rolled over Dallas, Texas. This wasn't a hurricane, it was a downburst, a concentrated localized blast of air slamming the ground at 73 miles per hour. A tower crane on the Ellen City Lights apartment complex was struck by this sudden violent force. It did not weather vane. The wind caught the crane's jib broadside, locking it in place and applying a force the mast was never designed to take. With a horrifying sound, the mast buckled. The entire crane, counterweights and all, toppled over, slicing through the adjacent apartment buildings as if it were cardboard. The tragedy cost 1 life and injured 5 others. The subsequent NTSB investigation revealed the horrifying, simple truth: the slew brake was engaged. We may never know if it was a mechanical fault or an operator error, but it didn't matter. That single locked brake turned a brilliant flexible piece of engineering into a rigid 500-foot lever. All the grade 50 steel, all the bedrock anchors, all the aerodynamic design, all of it was rendered useless. The crane could not turn, it could not flex, and it could not surrender. Faced with a force it was never meant to fight, it was simply and tragically broken. These failures are brutal reminders that the laws of physics are absolute. They are the exceptions that prove the rule, that a tower crane's survival hangs on a delicate, engineered balance between immense strength and, above all, the wisdom to surrender. Thanks for watching Hard Hat Industries, your source for serious machines doing real work. If you like this, hit like, subscribe, and turn on notifications so you don't miss what's next. Until then, keep your head down and your gear running.